Hello class. So in this video we'll be talking about solving non-homogeneous ordinary differential equation. Right, so the new thing here is that the equation will include the external driving force. That's this term. Okay. So the homogeneous one we have just discussed in the previous class. But now we'll prepare ourselves when the system being driven. And they call non-homogeneous because the right-hand side has additional term that is not depending on the position as is coming from some external force. Right, so there are two important properties, new properties that we need to remind you, okay, for handling the non-homogeneous ordinary differential equation. First, if you assume XH is a solution for the homogeneous one, and XS is a solution to the non-homogeneous equation, and otherwise they have the same form, then we can show that even the superposition, okay, is also the solution of the non-homogeneous differential equation. You can show that easily just by adding these two together. Okay, and then you see on the left hand side, the two functions are added together. On the right hand side, 0 plus f is also f. Okay, so what that means is that the general solution of the non-homogeneous equation will also include the solution of the homogeneous equation. For example, in the previous class, we talked about the solution to the homogeneous equation can be written as something like this, where alpha 1, alpha 2 are the two roots of this quadratic equation. Okay, so and now the general form of the non-homogeneous equation can also naturally include this the solution from the homogeneous equation. Okay, and we also know that for second order differential equation, you only need two kind of degrees of freedom. So now you already had the 2 degrees of freedom. So that means there's no more degrees of freedom left for XS. And this is why this part is kind of special, different from the other two. So that we use subscript S. It's called a spatial solution. Okay, so this spatial solution XS has no more degrees of freedom, meaning it's fully given by this f of t. Okay, fully given by f of t, and the spatial. Okay, and we don't need to. There's no more degrees of freedom we need to worry about. All right. So the second important property of this part is that this if you consider one so let me go back to the right pen. Okay, if XS1 is a spatial solution for F1, so you want to solve a solution for F1, you also want to solve the solution for F2. It turns out then the sum of these two solutions will also be the solution if the external force is the sum of the two forces. Okay. And this again is because the equation is linear. Okay, you can write down the equation for F1, write the equation for F2, and add the two equations together. You can show that XS1 plus XS2 will also be the solution. Okay, if the total force given by the sum of the two forces. All right. Okay. So, and we want to mention this property because we would like to kind of solve the equation in a straightforward way. Okay. So, assuming now we want to find a solution for this non-homogeneous equation. Okay, and then a cosine on the other side. Then we can try to supplement it with a second differential equation where we want to know the solution for sine. Okay. Now, because the equation is linear, we can add them together. But instead of just directly add them together, we multiply the second term, the second equation by I, and then add them together. So the first term becomes x plus iy, okay, and the second derivative. Second term is x plus iy and the first derivative. Okay, the last term is x plus iy. And then the right hand side, you have cosine omega t plus I sine omega t. So the right hand side becomes ei omega t. So this is the right hand side, become ei omega t. Okay, and since we always have x plus iy, that define this complex displacement x tilde, okay, to be x plus iy. So instead, well, we can start with an equation like this one. Let's try to solve this equation. And then the real part, once you solve the equation, you know x tilde. Okay, the real solution is the real part of that solution would then be the solution of the original equation. Okay, of the original equation. Right. So essentially, this we can first go to the complex plane, go to complex number. But always remember, okay, what we want to solve is the real part. Okay. So once you solve it, and then we can go back to the real part to know that the solution we desire. Similarly, once you get a complex solution, you can also get the imaginary part. See, imaginary part satisfies this equation, so imaginary part of the solution will also be the solution when the driving force is A sine omega t. Okay, that's a equation. The imaginary power of the x tilde will satisfy this second equation. So what's the point to go to the complex plane, complex number, and come back, take the real part? Why don't we just stick to the real part, the real number for the, why do we need to go to complex? All right, so yeah, two reasons. One is that when we go to this with a complex number, okay, we can essentially solve two equations at once. We not only know the response when the driving force is cosine omega t, use a different color, cosine omega t. We also know the response of the system when the driving force is sine omega t. Okay, but then you might ask, why do you even need to care about sine omega t if the question, if I'm asked to solve this solution with cosine omega t? So actually the real reason is I'm going to show you this, if you go to complex number calculation, it's much easier. It's much simpler, okay, but you need to do one extra step when you solve it, and remember to take the real part, which is not too hard. Alright, so let's consider this equation you want to solve. The driving force cosine omega t. Okay. This corresponds to a harmonic oscillator because and with a damping and also being externally driven. Okay, and this external force driving the pendulum, driving the oscillator. So first, try to go to the extend this from the real equation into the complex equation, complex differential equation. So replace x by x tilde, and the tilde just remind us. Okay, some textbook you don't even need to don't even remind you anymore. Just use x. But for here, just to distinguish the two, we use x tilde to remind us the x, the displacement here is a complex number. Right, and cosine omega t also generalized into ei omega t. Essentially, what we do is just by adding a second sine omega t equation into here. All right, so now let's try to solve this equation, the second one. All right, so a tip for the spatial solution is a bit different, but very similar. Since the driving force ei omega t, we also assume the response, the solution is also going to be something like amplitude ei omega t. Okay, and the reason we have this kind of insight is because whenever you do the differentiation, my pen doesn't work again. Right, when you do the differentiation, you always get ei omega t, ei omega t, ei omega t, no matter how many times you differentiate. Come on. Alright. Okay, but just remind ourselves here x tilde and a can in general they're both complex numbers. Okay, and the good thing about this ei omega t is that not only you have identical factor here, but actually the same factor on the right hand side. Alright, because right hand side also ei omega t. So now you see now this is kind of a reason. Okay, we have this kind of trial function, so all this can be cancelled because ei omega t never go to 0. Okay. All right. So when you cancel all, then you are left a. You can factor it out, and the residual you put into this bracket. No, so we got the amplitude. Okay. Then once you do this, once you figure what a is, you can plug again back to the original trial function back here. Why is my pen working so badly? All right, so this is a solution. Okay, so now you see a is nothing but f divided by this whole thing. So this is a new amplitude. It's a complex amplitude. And then we also have the ei omega t that we assume. Okay. All right. So this is a solution to the complex equation. But as we discussed, we only need to take the real part, and that will be the desired solution for the real differential equation. So you take the real part of this, you need to be careful because both this complex number is a product of two complex numbers. Use a different color. Here's a complex number. Here's yet another complex number. Okay, I'm just going to skip these details. Okay, it turns out this the complex number here. One way to quickly get the answer is I will look at complex number in the denominator. Okay, it just is a complex number. You can write it in the kind of complex plane. Change another pen. No, this also doesn't work. Come on. All right. Really bad pen. What's going on here? Maybe my finger is better than that. Alright, going to use my finger for now. So here you can see the complex number has a real part that's proportional omega naught minus omega square. Omega naught square minus omega square. Imaginary part is omega gamma. Okay, so if you want to know the absolute value, okay, then that will be rho. Okay, and then that turns out to be amplitude in the denominator, and then also the phase. So those are the phase. But now because this is in denominator, when you flip it to the numerator, now phase this ei phi becomes e minus I phi. 1 over ei phi is e2 minus I phi. Okay, so we define the phase this way, and then you have additional phase. Okay, that can be put into the second part, cosine omega t. So therefore you get cosine omega t. This will multiply together. Okay, you get cosine omega t minus phi, where phi is given in this diagram. All right. So that's a solution. That's a spatial solution. Okay. All right. Get this way. Spatial solution here. All right. So and also notice that both the amplitude oscillation and also the phi are given. Indeed, there's no more degrees of freedom. We don't have the choice. Okay, amplitude and phase are both fully determined by the equation. So to conclude on the math part, okay, so this equation we want to solve. Okay, and then we go to complex plane and take real part and so on, and eventually get a solution looks like this. And this is a homogeneous solution. Okay, any additional homogeneous solution, we also have a special solution that we just derive. And that will be the most general solution. Okay, and what is so special about this is also that it's fully determined by the driving force, and it doesn't, in general, it doesn't decay. Okay. On the other hand, as long as any damping gamma larger than 0, homogeneous solution in no way decays. Okay, so this term, in the presence of the friction, will always decay. So after a long time, this term is gone. Okay. So if we wait for long enough time, then the solution will be left with only the special solution, okay, which is this part. Okay. And then to rig this into kind of take the real part and convert this into cosine omega t. Okay, you know, to compare with a kind of a real quantity. Okay, and then for the kind of real solution. Okay, that's it for this class. Bye bye.